Hi Jeffrey,
Hi,
how are you? How is your week?
I've been doing pretty well. Um, it's not too much other than work has been happening. How about you?
Uh, I was thinking that I will fine, but actually I just remember that in the midterm exam, in the question three, I make a mistake at the beginning in the per hit.
Uh,
Then I dragged that mistake until the end, so it's like, oh, come on. But besides that, I think that everything is fine.
yeah,
Yeah.
I guess yeah, I think it's really unfortunate because I think yeah, it was question three, right? That had yeah,
Well,
I,
actually,
that,
my mistake was that instead of considering 2 to the minus theta, that
right.
is equal to zero point 0.5 to the theta. I took the complement. So for me it was 1 minus zero point 0.5 to the theta. It was the other part of the CDF. But well, I think that that kind of thing sometimes happens, right? So the best thing I can do is learn from that mistake
Yeah,
to avoid repeating it in the second midterm or in the final exam. I don't know.
yeah, absolutely.
What are we going to see today, Jeffrey?
Today will be a kind of introduction to the next unit, which is hypothesis testing. So,
Mhm.
uh, I guess we had a somewhat foundational intro in at the end of unit two. But this time we're going to be looking at more specific hypothesis tests when we were dealing with some more edge cases or
Okay,
building off of stuff from unit three.
okay. Jeffrey, actually, uh, when I was trying to study, I I had this book that is named All of Statistics, but sometimes some topics are not deep enough. Do you know any other reference that I can consult to that is more at the same level of the course that we are taking right now, or that is the best book I can have right now?
Um, I'm not too sure what recommendations I could give. Sorry about that.
No, that's fine.
Um, well, um, I am from the third cohort, but I couldn't uh, attend to the class of yesterday. So I am here. My name is Ana Cruz, and this is my first and I hope my only class because I want to be um, on the day with my other group. Hello.
I see. Yeah, well, welcome to this recitation.
Welcome, Anna. I think that
Thank
we've
you.
been in a breakout room together once. I think that the second time that we have this class, the second cohort and the third cohort were together.
Oh, great. A friend advice. Nice. Jeffrey, I also have a question, and it was about the final exam, not this exam, the at the end of all the courses, we take an exam. Do you have some recommendations in order to practice for that exam? I don't know. I don't remember the name. It's
Capstone?
yes, the capstone.
Hello, everybody.
Hello, Cynthia.
Hello. Yeah, so I actually held a capstone review session for people from previous year. I think what I was told was generally the focus will be on the material that we've gone over so far. So basically from so basically uh unit two, which is basically the statistical inference stuff. and then Unit 3, methods of estimation, along with Unit 4, which is the next unit that we'll cover, which is hypothesis testing. And there'll be a little bit of Unit 6, which is linear regression. Or at least like this is what I was told when helping prepare for that session. So I imagine it'll probably be somewhat similar for you guys as well. When you guys like take it like at some point in the future.
Okay. Yes, maybe the next, well, in my case, the next year, I'm going to take the capstone.
I think that for the second cohort, the capstone will be in November or something like that, near November. So
yeah, I guess it's definitely good to be thinking about these things at some point, I guess.
for me, the most complicated part about the capstone is going to be that the first course that I have taken. I took it like a year ago, so it will be kind of difficult to find the time to study again those topics, or just to remember what have I done like a year ago. But actually, I think that all these courses are really related. So if I successfully complete this course, I think that it would be really easy to go back to the first course and solve the problems.
Yeah, hopefully like it's like hopefully like these courses have been like at least like building off of each other like fairly well, so that
Yes, I remember that in the first course. That's stop.
yeah. Cool. I think we have quite a few people today, but I guess I'll take around 1 or 2 more minutes just to see if more people come before starting. Yeah. Let's see. Cool. So it looks like we have around 12 or so students today. So, or at least like right now. So let's get started. Let me share my screen. Cool. So hopefully everyone is able to see this. Can people give me a thumbs up if they can see this?
Yes, we can see it.
Cool. Yeah, so hello everyone. Welcome back to 186501 recitations. Yeah, so last time we did midterm review, and so congrats on making it through the midterm. I think there were a few forum posts asking when results would come out. I'm not too sure when like specifically like scores will be out. They might already be out. I'm not 100% caught up on this. But if they're not out yet, results they should be out within a few days. And yeah, hopefully everyone thought that they did well, or at least thought that the midterm was a pretty good like learning experience, based on based on how people discussed it like before, just before this recitation. But yeah, so moving on from the midterm, today we'll start our main hypothesis testing unit, which is unit 4. So in this case, we'll kind of be moving away from, we'll still have like aspects of our or stuff that we talked about from unit 2, such as like the basic terminology and kind of like the usual the tests that we kind of looked at in unit 2, which mostly like relied on the asymptotic normality of certain estimators. But here we'll take this a little bit further and talk about more specific tests that we might be able to apply, kind of like building off of stuff that we discussed in unit 2 and also unit 3 actually. So our warm-up here will be reviewing some of the concepts in hypothesis testing, because even though there probably was a little bit of hypothesis testing in the midterm, it's still kind of good to at least review the like foundational terms in hypothesis testing, or the foundational ideas. Cool, so let's get started. All right, so yeah, so let's kind of review the overall idea behind hypothesis testing. So let's look at the first question on the recitation worksheet. Hopefully everyone has the recitation worksheet, but if not, I can also paste it into the chat. Cool. So our first question that we kind of want to ask about how hypothesis testing is, what is the overall goal of hypothesis testing? And for example, like what sorts of conclusions can we draw from doing hypothesis testing? So cool. So take a minute or two to think about this. Hopefully this should be kind of like a review of material from previous weeks. And yeah, feel free to type your answers into the chat or unmute and say your answer. Yeah, so I see an answer in the chat. How sure you are about a hypothesis. Yeah, I think that's part of the idea behind hypothesis testing. Check how likely something is. I think the second part, to be probable or not, might be a little bit redundant, but I think these two kind of capture the general idea of hypothesis testing, which is kind of like, we want to say something about the So remember that when we're looking at hypothesis testing, we always have kind of like a statistical model in mind where we're looking at a set of parameter distributions. And so often we want to say something directly about a parameter. So say something about a parameter. And more often than not, the something that we say about a parameter is called the hypothesis. And yeah, as another person, or as Sebastian also said in the chat, we want to kind of like test the hypothesis itself, or like how sure we are that the hypothesis is kind of true in some sense, or how probable it is that it is true. So yeah, test how probable right. But I think when we're actually like drawing conclusions from the hypothesis testing, we won't actually use the words like true or false. Instead, because we're dealing with more probabilistic statements, let's see. Yeah, so one of the conclusions that we can draw is that we reject the null hypothesis, which I think, let's see. Yeah, I think that's something that Sebastian also mentioned. If you can reject and don't have enough evidence to reject. So reject. And more specifically, what we're testing is the null hypothesis against the alternative hypothesis. But we can kind of like review these terminology as well after this. So reject the null hypothesis and fail to reject the null hypothesis. Right. So one of the key things here to keep in mind is that, yeah, so the like fail to reject is something to like, that's like pretty important, because we don't like accept the null hypothesis when we fail to reject. We can only say that we don't have enough evidence that the null hypothesis isn't true. So yeah. So generally, when we're talking about hypothesis testing, we won't use the word like accept. Similarly, we won't say something like, we won't say the words true or false, because they kind of denote like some sort of certainty involved in the conclusions that we're making. And generally, we're dealing with like probabilities when we're talking about hypothesis testing. Cool. So yeah, so hopefully that gives you that is kind of like a review of the overall goal of hypothesis testing. So let's move on slightly to a review of the terminology. Let's see, I can probably keep this. Actually, yeah. So kind of recall like all of the like foundational terminology that we discussed. So first is the hypotheses. And we had the null hypothesis and the alternative hypothesis. And remember that we used H0 and H1 to denote these hypotheses. And remember that you can kind of think of the null hypothesis as being like the status quo, the thing that you're trying to say is, or you're testing is, might not be true. Status quo. And the alternative hypothesis is the, as it kind of like has in its name, like the alternative to the status quo. Right. So whenever we're doing a hypothesis test, we'll have these two hypotheses, and we're going to be testing H naught against H1, I believe. And so whenever we do a hypothesis test, we'll have an actual test itself, test, which we denote using the Greek letter psi. And so this will be, this will kind of be an indicator variable, which will be equal to, let's see. Sorry. Right. So it'll be equal to 1 whenever we reject the null hypothesis, and it'll be equal to 0 when we don't reject. So 1 if reject, 0 if fail to reject. And with the test, we have an associated rejection region. Rejection region, which we'll denote with an R and bar. And so this will be kind of like the region where the test will reject. Where in this case, the region is kind of like a subset, or kind of like a subspace of the event space of E to the N, where E denotes the event or the sample space. Cool. And so generally, when we're doing hypothesis testing, we'll have to keep like, there's also like some additional things that we have to keep in mind, such as whether or not whether our test is one-sided or two-sided. One-sided versus two-sided. So generally, one-sided means that when we're looking at some distribution, we're only looking towards like one side of the distribution. Whereas if we're looking at a two-sided test, we'll kind of have be looking towards both extremes. So this area and this area. And similarly, we maybe want to keep in mind whether or not our test is a one sample test or a two sample test. One sample versus two sample. And so maybe one sample, we want to say something about one particular distribution. And maybe for two samples, we want to say something about the parameters of two different distributions that come from the same statistical model. And lastly, we have type 1 error and level, along with type 2 error and power. Cool. Does someone want to remind everyone what type 1 error and type 2 error are? Feel free to answer in the chat.
Jeffrey, I think that the type 1 error is when you reject the hypothesis when it's true, and the type 2 error is when you fail to reject the hypothesis when it's false.
Right. So, yeah. So as a reminder, the type 1 error is because one way to think about it is that it's associated with a level, which, yeah. And essentially, the type 1 error is the probability that we reject the null hypothesis when the null hypothesis is actually true. So and on the flip side, the type 2 error is a probability that we fail to reject the null hypothesis when the alternative hypothesis is true. Right. So in this case, we do use the words like true and this is mostly because we're not necessarily like drawing conclusions from the hypothesis testing, but rather saying stuff about like conditional probabilities when like H naught happens to be true and when H1 happens to be true. Right. So along those lines, we can say that the level is essentially like an upper bound on the type 1 error. And generally, when we're looking at type 1 errors, or actually a lot of times when we're looking at type 1 errors, we generally have a null hypothesis that's of some form like theta equals a specific value like theta naught. And in those cases, it's simply the type 1 error at the point that we're looking at. But sometimes it might be a little bit more complicated than that. And similarly, the power is essentially like 1 minus the lower bound on the type 2 error. So this is,
Hi, Jeffrey.
yep.
This is Cynthia. I have a question about one-sided and two-sided. My question is, what is the main factor that decide if hypothesis is one or two-sided? For instance, let's suppose that we have our null hypothesis equal to 4. The alternative hypothesis equal to greater than 4. This will be one or two-sided.
Right. So generally, when we're determining how many sides a hypothesis or a test has, we will typically be looking at what form the alternative hypothesis has. So generally, for one-sided, these will kind of be sort of like inequalities of the form like theta is less than or equal to some value theta naught, or theta is greater than or equal to some value theta naught. So in your example where theta is, where you want to test like whether or not theta is greater than or equal to 4, in that case, that would be a one-sided test because generally we're looking towards one extreme rather than like both extremes.
Okay, but in my example, it was the alternative hypothesis was greater than 4 and the null hypothesis was equal to 4. So we can conclude that the main factor is the alternative hypothesis. We have to see the alternative hypothesis in order to decide if it has one or two sides.
Sorry, can you repeat that?
I mean, in the example that I gave you was we have the null hypothesis equal to 4, equal to certain number, equal to certain null. And the alternative hypothesis was our theta greater than 4.
Yeah.
So we have the null hypothesis equal to certain number and the alternative hypothesis greater than certain number.
Right.
In this case, I have a doubt about, I don't know if the hypothesis is one-sided because the alternative hypothesis or is two-sided because the null hypothesis.
Right. So generally speaking, generally speaking, we determine the number of sides based on the alternative hypothesis.
Okay.
Yeah. So sometimes it is possible that we do have tests, as you mentioned, where like the null hypothesis is like equal, has like our parameter equal to some value. And that's mostly because we're kind of like shortcutting in some sense where we're like assuming that theta cannot be less than 4 for whatever reason. Or that it's like very unlikely that it'll happen. But generally speaking, we determine the number of sides based on the alternative hypothesis.
Okay. Thank you so much.
Yep. Yeah. Does anyone have any other questions about the terminology? Cool. So in that case, let's move on to a short breakout room exercise, just to get you all thinking about the terminology again and how you might be able to set up your own hypothesis test. So yeah, so in breakout rooms, what I want you guys to do is to give an example of a hypothesis test. So in this case, make sure you understand what the null hypothesis is, the alternative hypothesis is, and the region theta naught and theta 1, or big theta naught and big theta 1 in a parameter space corresponding to the two hypotheses. And if you can, try to also design maybe a test statistic for this, where generally speaking, the test statistic will be involved in our actual test and perhaps our rejection region as well. Cool. So let's spend about 3 to 5 minutes. I'm going to set up breakout rooms now. Let's see. Cool. Let's see. Okay. Cool. I will open breakout rooms now. Try to, in your groups, come up with a hypothesis test, including noting what the null and alternate hypotheses are, and perhaps coming up with a test statistic and the corresponding test and rejection region, if you can. All right, so now that people are back, would anyone like to give an example of a hypothesis test that their group came up with? So feel free to unmute yourself and talk me through the aspects of the hypothesis test that you guys came up with, or feel free to put it in the chat.
I think that one example of the hypothesis test might be that the runners in these Olympic Games are faster than the runners in the last Olympic Games.
So runners in Olympics
Mhm.
versus runners where?
So the runners in Olympics in Tokyo 2020, I think is the name, versus runners in the last Olympics
Oh,
that I don't remember where it was or what was
I
the
see.
year.
So you want to test whether or not runners in this Olympics have
Or it might be another kind of comparison. It might be Olympics versus the athleticism mundial or something like that.
runners in movies, or
And in the World Championship of athleticism.
I see.
And another hypothesis test could be if a vaccine is effective or not. And you can consider like it's effective if you can demonstrate or maybe think that it's 90% or 90% of people develop some, I don't know how to say this. Well, more than 90% of people.
Right. So we have like two examples here. One of which will kind of involve. Okay, so let's actually talk, I guess, like talk through both of these examples because these both might be pretty illustrative.
Yes, but I have it's not another example. It's about what Anna said. We can test whether or not the vaccine is effective, or we have to put a boundary there, like 90%, 95%.
Yeah. So generally, when we're like running hypothesis tests, because we're dealing with data, we'll often want to have like specific like boundaries at least. So one possible way to put a boundary on this is like say maybe we want to compare it to like a specific percentage, like this is like effective like 90% of the time or something. Another way to do this is to maybe compare it to a placebo, such as like, oh, suppose like we have like some shot, we have some like control shot that like doesn't really do much versus like our actual vaccine, and we kind of want to compare these two, the two effectiveness there. So those are like kind of two ways to put like boundaries in some sense.
Okay, thanks.
Yeah. Cool. So let's kind of walk through maybe these two examples. So the first one, we notice that like we're kind of like comparing two different like populations in some sense, or at least like two different versions of, maybe there's like some overlapping population, but like there's some like time difference that makes it so that they're kind of different. So in this case, suppose like we're comparing the two kind of like means of the runner times. So in this case, maybe this is mu1 and this is mu2. And so maybe our null hypothesis is going to be, say, the runners maybe haven't improved at all. So like mu1 equals mu2. And our alternative hypothesis is maybe that, you know, either the runners have improved since the last Olympics, or the runners at our Olympics 2020 are better than runners elsewhere. So in this case, this would be like mu1 is less than or equal to mu2. So yeah, so I guess in this case, like having a lower mean means that you are able to run some distance faster. So running time. And so maybe we might have enough samples so that, you know, some more asymptotic tools might apply here. So we could design a test statistic to be like of the form mu1 minus mu2 divided by, let's see. So in this case, if we're assuming that the two distributions are normal, assume distributions are normal, then we might have some variance estimator. So hat sigma 1 squared divided by n plus hat sigma 2 squared over m. And so this might be the test statistic that we're looking at. And it might be approximately a normal 0-1 distribution. And so in this case, we could compare the test statistic to some quantile to see whether or not we have significant evidence that the runners have improved or the runners are better. And so this is kind of an example of a two-sample hypothesis test. So two-sample. Because notice that we're drawing two different samples, possibly with different sizes from two different populations. And similarly, this is a one-sided test. Because like kind of as was discussed earlier, even though we do have a null hypothesis where mu1 is equal to mu2, we generally look at the alternative hypothesis to determine whether or not it is one-sided or two-sided. And in this case, we do have this inequality here, which is less than or equal to rather than a not equal sign. Cool. And so similarly for the other test, suppose we wanted to say whether or not a vaccine is, say, at least like 90% effective. Suppose we had some way to quantify the effectiveness of a vaccine. And so we might have some parameter theta naught controlling, which is like kind of like the rate of effectiveness of the vaccine. So in this case, our null hypothesis would be theta naught is less than or equal to 90, is less than or equal to 0.9. And our alternative hypothesis, sorry, it should be greater than, yeah, is theta naught is greater than 0.9. And similarly, we could design a test statistic for this. It would probably look something like, oops, these should be hats, sorry. It would be something like hat theta naught minus 0.9 divided by whatever our sample variance is. Yeah, actually, I guess something I'm also missing in these test statistics is that there is also a square root n factor as well. Actually, let's see. Yeah, actually, I think for the first test, there isn't necessarily a factor of square root n because I think this is captured in the denominator, but for the second one, there might be a like square root n here. And once again, we might say that this is approximately a normal 0-1 distribution, assuming that we do have the conditions to perform our asymptotic normality tools, or use our asymptotic normality tools. And so if we were to look at this test a little bit more closely, we would also notice that this test is one-sided. Like our first test, because once again, our alternative hypothesis consists of this inequality statement greater than or equal to, or sorry, greater than, rather than a not equals to sign. Oops, okay. And the main difference I would say here is that this test is one sample, because we're kind of like only considering like one, we're only like using one sample here, or we're only drawing one sample from some specific population. Cool. So does anyone have any questions about these two examples?
Hello, Jeffrey. I have a question, but no with these examples. Is it possible that you make a null hypothesis where the parameter that you want to try, or you want to know if one parameter is between or is inside an closed interval?
Yes, I believe there are tests that do that. I think, I believe there might have been one in one of your homeworks where I think it was like some parameters between like, some parameter like theta is between 0.49 and 0.51. I think we call these like composite tests or something like that, where kind of our null hypothesis is a little bit more complicated. So yeah, it is possible to design tests like these. I think it ends up being a little bit more complicated to design our test statistic though. Yeah, does that help?
Okay.
Right. Actually, yeah, so this should be the square root of the variance, sorry, instead of the variance. Yeah, in order to make this approximately a standard normal. So this would be the standard deviation. Cool. Any other questions on terminology and these two examples? Cool. So we'll actually be skipping the next three, or we'll be skipping the rest of the review exercises. And we'll move on into more complex tools that we use in testing. And these will be partially building off of what we went over in units 2 and 3. Yeah. Cool. So the first tool that we'll be looking at is actually a new distribution. And this distribution will play a fairly important role in the two tests that we'll hopefully be talking about this time. And so this is called the chi-squared distribution. Cool. So the chi-squared distribution has one parameter. And the parameter is generally has the variable name d, which denotes degrees of freedom. And we generally write the chi-square distribution as using this Greek letter, which looks like an X, but also has like a little bit of like a curl to it. Chi squared and subscript d. Cool. So how do we define the chi-square distribution? Well, we say that a random variable x is distributed according to a chi-square distribution if x has a distribution given by the following. The following sum from I equals 1 to d of zi squared. Another way of writing this is z1 squared plus z2 squared plus so on until zd squared, where each of the zi's, or the z1 so on until zd, is IID distributed according to a normal 0, 1 distribution, or each of the zi's is a standard normal random variable. Cool. So it might not be immediately obvious why defining this distribution would be helpful, and it certainly looks like this distribution is defined like in a somewhat complicated way, but we can kind of think of this as helping capture the distribution of the sample variance of some number of standard univariate normal random variables. Oops. Of some number of zi. So in this case, we would be looking at, like, for example, the sum of zi minus bar zn squared. And this chi-square distribution might help capture the distribution that this sample variance follows. And similarly, another way of like interpreting this is that it might be the distribution of the norm of a standard multivariate normal random variable. So of use C, I guess. So actually, let's use X. And D 0 ID. Yeah, so these are two possible ways of perhaps like interpreting the chi-square distribution. One of which is it might be the distribution of the sample variance of some number of standard normal random variables, Another way of interpreting this is it might be the distribution of the norm of some standard multivariate normal random vector, because each of the components of this random vector would be independent of each other, and they each follow a standard normal distribution. And remember that when we're taking the norms, we're taking the squares of each of the components and adding them up. Cool. And yeah, so I'm not too sure how many of you have seen this distribution before, but it might help to look at a picture of this chi-square distribution and see how it changes as the number of degrees of freedom increases. So let's move over to Wikipedia. And so this is kind of a picture of the chi-square distribution with different numbers of degrees of freedom. And so you'll kind of notice that when the number of degrees of freedom is pretty small, it's very heavily centered, or it's very, there's like, the distribution is very heavily, I guess, like centered. Centered might not be the right word here, but there's a lot of density at around like 0 or 1 or so. But as the number of degrees of freedom increases, it slowly starts to flatten out, as you can kind of see as you change from the yellow to the green to the blue, for example. And you'll notice that the center of mass, or kind of like where the mean or median is, starts to shift towards the right. Cool. Yeah. Cool. So that's hopefully a high-level overview of the chi-square distribution. So let's go through a few exercises involving the chi-square distribution. We'll first do these exercises in breakout rooms for around 7 to 10 minutes, and we'll go have a poll for these exercises afterwards to see where we're at. Cool. So hopefully you do have access to the recitation worksheet, and so you're able to see these exercises, but I'll still write them up here. So in the following problem, let x be distributed according to a chi-square distribution with d degrees of freedom. So the first question is, what is the smallest sample space of x? Where smallest means that we can't take anything away from the sample space without making it an invalid sample space for x. And the next two questions involve the expected value and the variance of x. And finally, we have this setup where we have x1 through xn are IID distributed according to a chi-squared distribution with d degrees of freedom. And what is the distribution of the sample mean? Bar xn. This one actually might be a little bit surprising, but the result should hopefully be fairly nice when you find it. And so as kind of a follow-up to this, if D equals 2 and N equals 5, what is the probability that bar Xn is greater than or equal to 3? Cool. Does everyone understand all of these exercises, or at least like understand what is being asked of these exercises? Cool. So let's open up breakout rooms again. And I'll give you around 7 to 10 minutes to work through these exercises, and then we'll go over these together as a class. All right. All right. So now that everyone is back, let's see how the discussions went, or how everyone feels about these through a Google poll. So this Google poll will be asking the same questions that are asked above. So yeah, feel free to answer the Google poll with the answers that you discuss within your group. And we'll see how all the groups did. If you weren't able to get through all of the questions, say like you weren't able to get through 2D, you can feel free to leave that blank and still submit the rest. Also, even if you were in the same group as someone who did submit, you can still feel free to submit your response as well. Yeah, and I'll give around 30 more seconds for people to submit their responses. Cool. So let's see how people did. All right. So it looks like most people were able to come to a consensus on the first 3 questions or so. I think most people said that the sample space of X is all non-negative real numbers, or at least most people said that, with a few other answers. Let's see. So most people said that the mean is D, and the variance is 2D, and it seems like there's definitely quite a split among which is the closest to the answer for the last question. Cool. So let's go back to the other screen. Cool. And so let's talk through these a little bit. So the first one, it is true that the smallest sample space of X is the set of all non-negative real numbers. I think technically the poll didn't necessarily specify that it had to be the smallest. So in some sense, the set of real numbers can also be seen as the sample space, even though you don't really reach the set of negative real numbers. So I wouldn't necessarily put that as part of the sample space. So yeah, I would generally go with the set of non-negative real numbers and technically maybe the set of real numbers, but I wouldn't really say that the sample space here would be any of the other choices which involved higher dimensions. Right. So now let's talk about some of the maybe things related to the moments of a chi-square distribution. So first, let's talk about what the expected value is. So I think for both of these, it's generally pretty helpful to write this out in terms of the definition of a chi-square distribution, or the random variable associated with a chi-square distribution. So in this case, x would be expressed as the sum of squares of normal random variables. So in this case, we could write this as the expected value of z1 squared plus z2 squared plus z3 squared plus so on until zd squared. And so by the law, linearity of expectation, we could write this as the sum I equals 1 to d of the expected value of z1 squared or zi squared. And because these are all IID, or the zi are all IID standard normal random variables, and the second moment here would be equal to 1. This would mean that the sum would be equal to just like d copies of 1, which means that the expected value overall is equal to d. Cool. So that's the expected value out of the way. And now let's talk about the variance. So the variance is actually a little bit trickier, but let's similarly write out the definition of the random variable associated with the chi-square distribution. So we would get the variance of z1 squared plus z2 squared plus so on until zd squared. And now it looks like we might be a little bit stuck, but remember that the zi are all IID, which means that we are allowed to use the linearity of variance here. And so that means that we can essentially break this sum up into, or the variance of the sum into sums of variances. And so that means that we can write this as being equal to I equals 1 of d of the variance of zi squared. And once again, because all of the zi are identical, that means that we can say that this is equal to d times the variance of one of these zi squared. And so if you remember the definition of variance, we can write this as d times the expected value of zi to the fourth minus the expected value of zi squared, quantity squared. And if you remember, the expected value of the fourth moment, or the fourth moment, is equal to 3, and the second moment is equal to 1, which means that we get 3 minus 1 squared, which is 2, and then when we multiply that by d, we get 2d. Cool. And so lastly, we look at the distribution of the sample mean. And here it's actually, once again, very helpful to write out the xi's in terms of these standard normal random variables. So if we let xi equal to, if we were to write it out in terms of these standard normal random variables, we might say something like z I1 squared plus z I2 squared plus so on until z I d squared, where each of the z ij's is distributed according to an n01. Then when we look at the sample mean, bar xn, this is equal to 1 over n times the sum of the xi's. So I equals 1 to n. I guess in this case, it might, let's see. Yeah. Yeah, let's write it that way. And then when we apply the definition of each of the xi's being the sum of these like zij squares, we get 1 over n times the sum from I equals 1 to n. And then we have another sum because we're summing over d of these. So we use another index j equals 1 to d of z ij squared. Cool. We also have that these are IID. And now because the Zij are all IID because they're all like IID within the same xi's, and the xi's are all independent of each other and identically distributed. And so that means that because there are n times d of these normal random variables, that means that we can actually further write this as 1 over n times the sum from k equals 1. Let's use a different index k to d times n of zk squared. Because when we look inside this sum, we notice that there are n repetitions of d terms, which means that there's d times n terms overall. And so lastly, this means that using the definition of a chi-square distribution, this means that that this is distributed according to 1 over n times the chi-square distribution with dn degrees of freedom. And so in some sense, you're increasing the number of degrees of freedom by a multiplicative factor of n, but you're also dividing the output that you get by n. And so using this, if we plug in d equals 2 and n equals 5, we want the probability that if x is distributed according to a chi square distribution with 10 degrees of freedom, we want the probability that x is greater than or equal to 15. We get this from multiplying 3 by 5 because there was a 1 over n factor when we look at the sample mean. And so if you were to look at this in some chi-squared calculator online, you would get that this is around 0.132. All right, so these are the exercises for this part. Does anyone have any questions on any of the calculations here? are people generally satisfied with these calculations? Cool. So let's see.
Jeffrey, hi, I have one question.
Yeah.
If n is enough large, the mean could be normal, right? But as the sample space in this case is too small, n is equal to 5, we can approximate to a normal, right?
Yeah, so in this case, we can't, because like n is like very small, we can't use any like asymptotic normality statements. When n gets large, we can theoretically approximate this using a normal distribution, but when n is small, I guess generally speaking, we might prefer to use exact distributions, but yeah, especially in small cases, we have to use exact distributions. Cool. Does that help?
Yes, thanks.
Any other questions on these calculations? Cool. So actually leading off of what Sebastian asked, this will lead up into our first test that we're going to look at, which is the t-test. Yeah, so generally nowadays, I think it's like pretty easy to get your hands on large amounts of data. And so we're often able to use the asymptotic properties of our estimators because, you know, our sample spaces, our sample sizes are going to be really large. However, what happens when our sample size isn't that large? You might imagine that we potentially have limits on our sample size, either because the set from which we're sampling isn't that large, or we're like super constrained on the amount of time that we can spend sampling or something like that. So in this case, we'll often want to look at the exact distribution of our estimator based on the statistical model that we're using. So we'll be looking at one such example with the t-test. But first, it will help to introduce the t-distribution or the student's t-distribution. And so kind of like the chi-square distribution, we'll denote it with a lowercase t and the subscript d. And once again, the parameter here is d with degrees of freedom. Cool. And so we say that a random variable x is distributed according to a t distribution with d degrees of freedom. If x has a distribution given by this random quantity. Z over the square root of v divided by d, where z is a standard normal, v is a chi-square distribution with d degrees of freedom, and z, v are independent of each other. Cool. So this definition might look somewhat unintuitive, but generally, like, remember that we said that the chi-square distribution kind of helps capture the distribution of the sample variance. And so this is kind of where that like definition or that like interpretation kind of comes into play, as one can kind of think of this as the mean divided by the variance, or the standard deviation, sorry. Where there are going to be like some factors of D flying around here and there, but it all ends up working out in the end. And specifically, this is kind of like the mean divided by the variance for a Gaussian distribution, because the numerator is a standard Gaussian and the chi-square distribution is defined in terms of standard normal random variables. Yeah, and so because this distribution is defined like a little bit in a strange way, it's not clear what the picture of the distribution might look like. And so I'll also show you a few pictures of that with this. So, yeah, so this is a picture of the T distribution, where in this case, the nu, or the letter that looks like a V, is the number of degrees of freedom. And so feel free to type in the chat or feel free to unmute. So what observations do you notice can you make about the T distribution, particularly for like small values or as the number of degrees of freedom goes to infinity? Yeah, so feel free to say any observations in the chat or through voice. Right. So one of the observations that Sebastian made is as the number of degrees of freedom goes to infinity, which is actually asked in the recitation worksheet, this distribution will actually converge into a standard normal. Are there any other observations? Such as like what happens if the number of degrees of freedom is small? Actually, yeah. So one observation I might make here is that you'll notice that when the number of degrees of freedom is like kind of small, the center is kind of flattened a little bit, while the tails are a little bit more what we call heavy in some sense. And so we kind of call this like kind of distribution more tail heavy. This will kind of come up a bit later when we look at, for example, like QQ plus or other things like that. But yeah, so the observation I would make here is that as the number of degrees of freedom increases, the distribution becomes less tail heavy, which means that there's less values off to the tails of the distribution, and it starts to converge into a normal distribution. And kind of the reason why this converges to a normal distribution is if we look at the definition of the T distribution, you'll notice that when we looked at the expected value and the variance of the chi-square distribution, the expected value we saw was equal to D, and the variance is equal to 2D. And so when we divide this random variable following a chi-square distribution by D, that means that the expected value is going to decrease to 1, and the variance is going to decrease to 2 divided by D. And this 2 over D will go to 0 as n goes to infinity. So in some sense, you can say that V over D will converge in probability to the constant 1, which means that this distribution here will converge to a standard normal by Slutsky's. I believe that's the general reasoning or the general like correct reasoning behind why this kind of observation holds. Cool. So we kind of introduced this T distribution, and it's actually an exact distribution. So we're able to perform non-asymptotic tests on this. So generally, when we perform a one sample t-test, to kind of determine, to kind of like test our null and alternative hypotheses, we'll be looking at the test statistic Tn equals the square root of n times xn bar minus mu naught all over the square root of tilde Sn, where this tilde Sn is equal to 1 over n minus 1 times the sum of xi minus bar xn squared. And this is the unbiased estimator for the variance. Right. And so one additional assumption that we have to make here is that the x1 are, the xi are all IID distributed according to a normal distribution. Right. So notice the difference between our tilde Sn and our usual estimator for the variance, because in this case, the estimator involves a 1 over n minus 1, whereas our usual estimator for the variance might involve a 1 over n. Cool. So this leads us to our next poll question, which is under the null hypothesis. So suppose our hypothesis are like, suppose our null hypothesis was theta, or no, mu equals mu naught, and our alternative hypothesis was something like mu is not equal to mu naught. So under the null hypothesis, what distribution does this test statistic follow? And in particular, how many degrees of freedom are there if it follows some distribution with degrees of freedom that we talked about? So I'll put this poll in the chat. Feel free to answer this poll question. If you're not sure what the answer is, feel free to like make your best guess. Oh, also keep in mind that we're talking about the exact distribution. that might help a little bit. Well, I give about another 15 seconds for people to answer. Cool. Let's share poll results. Yeah, so it looks like most people do agree that this does end up being a T distribution. There is some minor disagreement about the number of degrees of freedom, but most people think that it's the T distribution with n-1 degrees of freedom. And this actually turns out to be the case. It is the T distribution with n-1 degrees of freedom. And this might seem a little strange because, you might expect it to have n degrees of freedom because there's, n samples. And it's like not immediately clear at first glance why we might lose 1 degree of freedom. But I would say that like the main reason might be because due to it has to do a little bit with the fact that the sample mean kind of puts a little bit of a constraint on the variance estimator that we're looking at. And so we end up losing 1 degree of freedom there. So this does follow a Tn-1. Yeah, so as kind of a remark, we might look at a similar test statistic when we're performing a 2-sample t-test. And you can kind of see that like this sort of test statistic is kind of similar to the test statistic that we looked at when we were looking at hypothesis tests earlier, which were like of the form like root n times some estimator minus our like value that we want to compare it to, all divided by the standard deviation estimator. And so, you might think, you might see how we might be able to design a 2-sample t-test instead. But in this case, when we're looking at the distribution that test statistic would follow, the number of degrees of freedom we are able to use is actually a bit more complicated. And is given by what's called the Welch-Satterthwaite formula. Hopefully I pronounced that correctly. But this is kind of a formula that we don't really expect you to memorize or use all that often. Generally, a kind of conservative estimate that you can use for the number of degrees of freedom is the minimum of the 2 sample sizes. Cool. And lastly, we might be able to discuss some of the advantages and disadvantages of the t-test. Yeah, so what thoughts do people have on the advantages and disadvantages of the t-test, if any? Well, I guess for starters, generally, because notice that when we discussed our test statistic, we said that our test statistic followed this exact distribution. And so what this means is that when we're designing a t-test, this test will actually be an exact test or a non-asymptotic test. Is a non-asymptotic test. And another thing is that notice that we didn't say anything about the sample size at all. And this actually kind of follows from this being a non-asymptotic test. The thing is that we're allowed to run this test even when the sample size is small. Yeah. And so you might be thinking like, oh, this is actually like a really nice test because, you know, it gives us like an actual like non-asymptotic test that we might be able to work with. There is one subtle disadvantage, however, and it might not be immediately clear, but the general idea is that this test only works when we do have this assumption that our that we're actually like drawing from a normal distribution. So this only works when xi is distributed according to a normal distribution. So in other words, we can't use this when our xi follows some like Bernoulli distribution or some Poisson distribution or exponential distribution. This only works when the xi follows some normal distribution. And so that's actually kind of like a strong assumption to make. We might be able to get away with saying, oh, the xi can somewhat follow a normal distribution or close to a normal distribution, but not quite. But we do need this like kind of assumption that the xi are distributed according to a normal distribution, or at least close to it. And later on, we'll kind of see how to test whether or not this is the case. Cool. So does anyone have any questions about this overview of the t-test? Cool. So,
Jeffrey, I have one question.
yeah.
Your unbiased estimator for the t-test is Sn, that is equal to 1/n-1, right? That n-1 has any impact on the test? I don't know, maybe when the sample size is small?
Let's see. So it turns out that we have to use this form in order to make sure that certain things work out and we end up with exactly the t distribution with n-1 degrees of freedom. So the 1/n-1 does like kind of make an impact that helps us ensure that we get this exact distribution. Does that like kind of help answer your question?
Yes.
Yeah. Any other questions? Cool. So in the remaining around 6 to 10 minutes or so, I'll introduce a little bit of the last test that we'll talk about, or that we'll introduce today, which is Wald's test. And so this will kind of use the interpretation that the second interpretation of the chi-square distribution that we talked about. So, right. Yeah, so the test statistic will kind of look roughly the same as what our test statistic usually looks like, but we might end up dealing with higher dimensional parameter spaces. So we do have a slight difference here. And the important thing to note about Wald's test is it's actually based off of the maximum likelihood estimator. So remember that we had, we were able to show that the maximum likelihood estimator is asymptotically normal back in unit 3. So this kind of suggests that we might be able to build a test off of the maximum likelihood estimator. So the setup for Wald's test is kind of the following. So let big theta be a subset of R to the D, denote the parameter space. So this is the parameter space. And let theta naught, so let theta naught be in our parameter space. So it's like some possible parameter. And so, so let x1, xn be IID distributed according to some p theta, where theta in theta naught is unknown. And we consider the hypothesis test where we're testing H naught and H1, where H naught is theta equals theta naught, and H1 is theta does not equal theta naught. So in this case, we want to determine whether or not our parameter is equal to some value in our parameter space. And notice that the key difference here is that our parameter might be multidimensional. And so this might cause some issues if we were to, try to look at our usual test statistic, because if at first it looks kind of hard to quantify, what is kind of like the distance in some sense between the two, the actual parameter and like the value that we're comparing. And so instead we consider this test statistic, Wn equals the norm of root n times I, the Fisher information. So I theta denotes the Fisher information. So I of theta naught to the 1/2 times hat theta MLE minus theta naught. And we consider the L2 norm, meaning that we look at each of the components and take the squares of those and add them together. And so the first question is, what is the asymptotic distribution of this test statistic under H naught? So to consider what the distribution of this test statistic might look like, let's think back to what we talked about or what we kind of like discussed in terms of the asymptotic normality of the MLE. So remember that when we looked at the asymptotic normality of the MLE, we had root n times theta hat MLE minus theta naught converges in distribution to a multivariate normal with d dimensions, with mean 0 and variance I of theta naught to the 1/2. Of course, this is assuming that the null hypothesis is true. So under H0. Oh, sorry. This is not quite true. This is I of theta to the inverse of the Fisher information. And so what does this mean? This means that if we were to multiply this by the kind of like the square roots of the Fisher information, where we kind of define the square root of a matrix to be the matrix such that if you were to square it, you would get the original matrix back. So if we were to multiply this by I theta naught to the 1/2, where this is the square root of Fisher information matrix. Right. So if we were if we were to consider like what would happen if we multiplied this would converge in distribution to multivariate normal with mean 0 and variance or covariance matrix I theta naught to the 1/2. And remember that, well, technically when we multiply a quantity by some matrix, let's see. Yeah, so the variance will get multiplied on both sides. One of the sides gets multiplied by the matrix itself, and the other side gets multiplied by the transpose of the matrix. But in this case, the transpose of the square root will happen to be equal to the square root itself. So that means that this ends up being I of theta naught to the 1/2 times the inverse of I of theta naught times I of theta naught to the 1/2. And so this means that when we're considering powers of I of theta naught, these end up being canceled out because 1/2 plus 1/2 plus minus 1 is equal to 0. And so this is equal to a normal distribution with mean 0 and covariance matrix, the identity matrix. And so kind of using this fact, when we can, this means that our test statistic, which will follow kind of this distribution or the norm of some random variable, some random vector following this distribution. This means that if we were to like take the norm of this, we would end up with this test statistic following a chi-square distribution with d degrees of freedom. Because essentially like each of the components of our random vector will be independent of all other components, and each component follows a standard normal distribution. And under the alternative hypothesis, this test statistic will simply diverge, essentially. And yeah, this is essentially the foundation for Walt's test. It turns out that you can replace this I of theta naught by also I of theta hat MLE, and this won't change the test statistic because of, or the asymptotic distribution of the test statistic because of convergence and probability. Cool. Any last questions about Walt's test or any of the other tests that we just tests or distributions that we discussed? Cool. So let's wrap up for today. Yeah, so as usual, I will send a link to the feedback form. If you have any feedback for me such as on the pace or the difficulty of the material covered in the recitation, along with any additional feedback that you have. But yeah, that's it for this time. Yeah, have a good rest of the week.
Okay, thank you so much. Have a nice weekend.
Thank you, Jeffrey.
Thank you.
You. Bye.
Good night.
Thanks. See you.